Hi, I welcome you to this lesson. In this lesson, we will learn about bits. In contrast, the binary number system, or what we usually refer to as the base 2 system. The essence of learning this is to let you understand how and why computers and other digital electronic systems communicates using zeros and ones. After this lesson, you will also understand how you can convert data from binary to decimal number system or the base 10 number system and vice versa. Again, knowing all these is a key to understanding computing and computer networking better. To begin, let's reflect for a few minutes on the previous lesson. In the previous lesson, we completed the part 2 of the OSI model lesson. We saw what the last 4 layers of the OSI model does to facilitate communication. We learned that the transport layer is responsible for port number addressing so that the right application receives right response from the right server. Again, we learned that the session layer also opens session to begin communication and closes them when communication is completed. We also spoke about the presentation layer being responsible for encryption, compression and encoding at the transmitting end, and decryption, decompression and decoding at the receiving end. And lastly, the application layer, which is the layer 7. Kindly watch the previous lesson if you have not done so, before continuing with this one. Now, let's go on to today's lesson. What is a bit? As said already in previous videos, a bit is the basic unit of information. Bit is the short form of binary digit, or the base 2 number system. A bit is either 0 or 1, and this is called the smallest unit of information in the computer. This is because every data fed into the computer is processed and interpreted by the computer as zeros and ones. Now, in digital electronics, signals exist as electrical charges, and this is in 2 states, that is either 0 or 1. 0 denotes the off state or the absence of an electrical signal, while 1 denotes the on state or the presence of an electrical signal. Before we delve deeper, let's note that, in this world, there is one most popular numbering system called the decimal numbering system, or what we usually call the base 10 system, from the basic school. This system starts its digits from 0 to 9, and we do combine these digits to get higher counting numbers. In a few moments, I will show you how we end up combining these digits to get whichever digits we want, but before that, let's also note that there is also another numbering system called the binary or base 2 system. And this is what digital signal processors use in processing data. So, your computer is one of them. Now, the question is, why do computers process data using zeros and ones, that is, the base 2 system, but not the popular base 10 system? The answer is that computer processors operate by using millions of electronic switches called transistors, each of which is either on or off. Similar to this, but much smaller. The state of the switch either on or off can represent binary information, such as yes or no, true or false, 1 or 0. Therefore, the binary digit that is bit is used. Although computers can represent varieties of information, every representation must finally be reduced to on and off states of a transistor. Thus, the answer is that computer does not have many states to store information, therefore, it stores information based on the 2 states of on and off, that is 1 and 0 respectively. Another question is, if a computer stores information in zeros and ones, how then is it able to recognize and store alphabets and even graphical symbols? The answer is that, in computing, there is something called character sets or character coding. Example is the ASCII character sets in ASCII Extended, which uses 7 and 8-bit of memory to store a single character. ASCII means American Standard Code for Information Interchange. In this code, alphabets, special character and symbols are represented by a unique decimal value which are then processed, understood and converted by your computer in binary. For an example, the word boy is understood by your computer in decimal as this. This is because the character, small b, is encoded by the computer as 98 in decimal, which is then converted and processed in binary as this. The character, small o, is also encoded by the computer as 111, which is converted and processed in binary as this. And lastly, the character, small y, is encoded by the computer as 121, which is then converted and processed by the computer in binary as this. So, each character occupies 8 bits, and a group of 8 bits is called byte. This is why 8-bit is equal to 1 byte. We are not going much into the detail of character sets in this lesson, but for a few moments, this is a table representing an ASCII character coding. Let me know in the comment section if you are interested in knowing the details of this, for me to cover the detail in subsequent videos. Now, going much into the detail of bits, let's now see how these bits work. To understand better the operations and counting of binary digit, we learn the basics from the counting of decimal digits, or the base 10 numerals. As we already know, the base 10 digits counts from 0 to 9. Now, to continue counting, we follow these set of rules. Rule 1. When you reach the highest digit, reset the column to 0, then increase the next column by 1. This is how we get the number 10 in decimal. Now, what I mean by increase the next column by 1 is that, to every counting number there are already preceding infinite number of zeros. Just that we don't usually write them because they are insignificant. So, we continue to increase the rightmost column digit by 1, till we get to the highest digit in that column. Here, we apply the next rule. Rule 2. When you increase the rightmost column digit by 1, carry down the preceding digits. And that is how we get the number 11, 12, 13, 14, 15, 16 to 19. At 19, we have gotten to the highest digit again in the rightmost column. So, we reset it to 0, then see if we can increase the preceding digit. Yes, we can increase the preceding digit by 1. And that is how we get the digit 20. Now, we can follow through this to get to whichever value we can count. Similarly, we can follow these same rules to count in base 2. As we know, base 2 digits starts from 0 to 1. So, we apply our first rule, as we have gotten to the highest digit. We then have to reset this column back to 0. Then we increase the next column by 1. As I said earlier, in every counting numbers there are infinite preceding number of zeros. That is how come we were able to increase this column by 1. Now, we can proceed to rule number 2. This column can now be increased to 1. And as this is increased to 1, rule number 2 then applies, so we carry down what is in this column. Again, we have reached the highest digit in both columns, so we have to reset both columns to 0. Then, we increase the preceding column to 1. As we continue, we can increase this by 1. Once we do that, rule 2 then applies, so we carry down these two columns. Now, in the next 10 seconds, go ahead, pause the video, and try your hands on the next 5 steps down to see if you can get them right. I will provide the answer shortly. Well, I hope you got them right. If not, let me explain. From here, we have reached the highest digit, so we apply rule 1 to reset this column to 0. We then see if we can increase this by 1. Yes, we can, so we increase this by 1. As we increase this by 1, rule 2 then applies, so we carry down this column. And that's how come we got 110 here. We had 111 also here because we can increase this by 1, and as we do that, rule 2 applies, so we carry down these two columns. And here, we have reached the highest digit in all the columns, so we reset all to zeros, and as we do that, rule 1 applies, so we increase here by 1. I believe you have understood now. Now, take a break and check something here. You can see that there are correlations between these binary digits and that of the decimal digits we counted earlier. So, these are the corresponding binary digits for the decimal digits we counted. To make it even more interesting, let's compare them this way. Here are the corresponding decimal values for these binary digits. In fact, we can continue on and on. Now, to easily convert or obtain corresponding binary digits for any decimal value, or vice versa, we can use the decimal place values or positional notations. For example, if I write this number in decimal, this is pronounced as 7,251. We can further interpret that 7 is in the 1000 place value, 2 is in the 100 place value, 5 is in the 10th place value, and 1 is in the ones place value. So, take a look at something here. As you can see, this denotes the ones decimal place value. And this denotes the 10th decimal place value. This denotes the 100 place value. This also denotes the 1000 place value in decimal. This denotes the 10,000 decimal place value. And this denotes the 100,000 decimal place value. So, we can pick out these corresponding decimal place values or positional values, and use them to obtain binary digit for any decimal number and vice versa. Taken some examples, we now make a table with the positional values like this. Now, from the counting we did, you could see that each positional value is 2 times the previous positional value. And the positions are 0, 1, 2, 3, 4, 5, and so forth. And this positional value is 2 times this one, this is 2 times this one, and this is also 2 times this one, same as this. So, that is how come we can take these values to obtain corresponding binary of any decimal number and vice versa. Let's now do some examples and see. Now, let's convert the decimal value 75 to binary digit. To do this, 1. Get the positional value that could be subtracted from the given decimal number. 2. If the subtraction is possible, turn on the bit for that positional value. In other words, the binary digit for that positional value becomes 1. And if the subtraction is impossible, turn off the bit for that positional value. In other words, the binary digit for that positional value becomes 0. Repeat the steps until the given decimal number is reduced 0. So which of these values could be subtracted from the number 75 as given? Let's start from the highest position, that is 128. No, we can't subtract 128 from 75, so we put 0 here. Next, 75 minus 64, yes, this is possible and we get 11, so we put 1 here. Now can we subtract 32 from 11? No, we can't, so we put 0 here. Next, we can't as well subtract 16 from 11, so we put 0 here too. Next, 11 minus 8 is possible. We get 3, so we put 1 here. Now 3 minus 4 is not possible, so we put 0 here. Next, 3 minus 2 is possible, so we put 1 here. Lastly, 1 minus 1 is also possible, so we put 1 here. This is the binary digits for the decimal value 75, and that is 0, 1, 0, 0, 1, 0, 1, 1. Let convert also decimal digit 100 to binary. We follow the same thing. Can we subtract 128 from 100? No. We can't, so we put 0 here. Next, 100 minus 64 is possible. We get 36, so we put 1 here. Next, 36 minus 32 is possible. We get 4, so we put 1 here. Next, we cannot subtract 16 from 4, so we put 0 here. 4 minus 8 is also not possible, so we put 0 here. Now, 4 minus 4 is possible, so we put 1 here. Lastly, we cannot subtract 2 and 1 from 0, so we put 0 here and here. So, binary digits for the decimal number 100 is 0, 1, 1, 0, 0, 1, 0, 0. Now, in a few moments, try your hands on this one and let's see. I will provide the answer shortly. Well, this is the answer, and I hope you got it correct. Let's work it out together. First of all, we subtract 128 from 150. It is possible, so we put 1 here. Now, we can't subtract 64 from 22, so we put 0 here. Again, we cannot subtract 32 from 22, so we put 0 here too. Now, we can subtract 16 from 22, so we put 1 here. We cannot subtract 8 from 6, so we put 0 here. Now, 6 minus 4 is possible, so we put 1 here. And 2 minus 2 is also possible, so we put 1 here. Lastly, we cannot subtract 1 from 0, so we put 0 here. This is how come we got the binary digit 100101110. In a short time, let's see another way we can convert decimal numeral to binary. In this method, we will keep dividing the given number repeatedly by 2 until we get 0 as the quotient. Then, we write the remainders in the reverse order to get the binary value of the given decimal number. So, let's convert same decimal numerals with this method. We start with 75. 75 divided by 2, we get 37, remainder 1. We then divide the quotient 37 by 2, we get 18, remainder 1. Now, 18 divided by 2, we get 9, remainder 0. 9 divided by 2, we get 4, remainder 1. Divide 4 by 2, we get 2, remainder 0. Now, 2 divided by 2, we get 1, remainder 0. 1 divided by 2, we get 0, remainder 1. Now, we write the remainders in the reverse order to get the binary value of the given decimal number 75. So, the binary digits for the decimal 75 is 1001011. This is same as this one because, remember there is preceding 0 here. Now, try your hands on the second one and let's see. I will provide the answer shortly. Well, I hope you had it correct. Let's work it out together. 100 divided by 2, we get 50, remainder 0. 50 divided by 2, we get 25, remainder 0. 25 divided by 2, we get 12, remainder 1. 12 divided by 2, we get 6, remainder 0. 6 divided by 2, we get 3, remainder 0. 3 divided by 2, we get 1, remainder 1. Now 1 divided by 2, we get 0, remainder 1. So, the binary equivalent of the decimal value 100 is 110010. And is same as this because of preceding 0. Let's now look at how we can convert these binary digits back to decimal. This is very simple. What we do here is, we sum up all the positional values such that is equal to the given decimal values. For example, converting these values to decimal, it becomes 64 plus 8 plus 2 plus 1, which gives us back the decimal value 75. Again, 64 plus 32 plus 4 will also give us 100. Another easy method is that we can use the positional notations. Therefore, the formula becomes the sum of the binary digits times 2 exponent their positions. Example: if we have to convert this binary digit to decimal, we can note the positions of these digits like this. Explaining further, we have to multiply 2 exponent the positional notation by each respective binary digit and sum them up. And following the formula, it then becomes 0 multiplied by 2 exponent 7 plus 1 multiplied by 2 exponent 6 plus 0 multiplied by 2 exponent 5 plus 0 multiplied by 2 exponent 4 plus 1 multiplied by 2 exponent 3 plus 0 multiplied by 2 exponent 2 plus 1 multiplied by 2 exponent 1 plus 1 multiplied by 2 exponent 0. Solving this out, we have 0 plus 64 plus 0 plus 0 plus 8 plus 0 plus 2 plus 1, and the answer is 75. Here, we got 1 because any number exponent 0 is 1. This is how you can convert binary back to decimal. Now, let's finally convert these binary digits to decimal. For the first one we still get 0. This is because, here, all the bits are 0. And for the second one, we get 255, because all the bits are 1. This is to say, for every 8 bits of binary digit, the lowest decimal value is 0, and the highest is 255. Please note these down. We will need this in subsequent lessons, especially in IP version 4 addressing. With respect to computer networking, this is what we use in assigning IP version 4 addresses to computers. We will get there, so don't worry. We end today's lesson here. Please subscribe to this channel if you find it helpful and share for others to watch. See you in the next lesson.